Okay, so we're going to go ahead and do an example using these steps right here to solve a first order linear equation. So, see, did I write down what it is? Yeah, it's example 2.3.1. And we're just finding the general solution to dy dx minus 3y is equal to 6. And so I said kind of like our first step of this type of method before we even start solving for it is just to make sure that it's in the proper form. But this one already is. We have dy dx minus something times y is equal to 6. So we've got p of x is equal to minus 3. And we've got f of x is equal to 6. So if p of x is equal to minus 3, then the integral of p of x dx is equal to the integral of minus 3 dx. So that's just minus 3x. And e to the integral of p of x dx is e to the minus 3x. So what I've done so far is I was given my differential equation in the right form, and I computed e to the integral p of x dx. So then I multiply both sides by that e to the minus 3x times dy dx minus 3y is equal to e to the minus 3x times 6. And then I say, okay, but I know from when we did that big long introduction to this section in class that e times dy dx minus p times y, is just going to give me d dx of e to the minus 3x times y. And you can go ahead and just always say that that's what happens. You don't have to show me those steps backwards. If it helps, just contact me and I can show that to you. But I'm going to go ahead and integrate everything. So integral of d dx e to the minus 3x times y dx is equal to e to the minus 3x times 6 dx. So when I showed you this example, where did I actually do it? When I showed you this example, I did integral of d times stuff. And sometimes students find that uncomfortable. So you can also think about it as I just integrate both sides with respect to x. So then sort of integrating a derivative cancels out, and I've got e to the minus 3x times y. And on the right-hand side, I'm integrating 6 e to the minus 3x dx. So that's going to give me, let's see, 6 times negative 1/3 e to the minus 3x plus a constant. So to find that integral, that was just sort of an exponential integral. So you divide by the derivative you would get coming out of that integral. And probably the hardest part in this section is going to be integrating exponents, because I know that it's been a while since you thought about that. And then finally, we can just solve for y. So we've got y is equal to, minus 6 over 3. E to the minus 3x divided by e to the minus 3x is just 1, plus c divided by e to the minus 3x, or times e to the positive 3x. Just like that. And remember just that when you took this integral right here, you had to have that constant of integration come out, same way as we did with separable equations, because if this was an initial value problem, you would have something like dy dx minus 3y equals 6 with y of 0 equals 3. And so if you found y equal to minus 6 over 3 plus c e to the 3x, I think we said, which is minus 2 plus c e to the 3x. Then you would just plug in your initial condition. So you would say, if I want y of 0 equals 3, then you have 3 is equal to minus 2 plus c e to the 3 times 0. So minus 2 plus c times 1. And you would find that c is 5. So the solution to the initial value problem is y equal to negative 2 plus 5 e to the 3x. To find just the general solution, that thing we found with the unknown constant in it was enough. I know that this whole general solution, initial value problem solution can kind of come out of nowhere. So think about that the general solution is all possible curves you could draw on your direction field. They're all things that follow the rules of your differential equation. Solution to IVP is one special curve from starting at the point x is 3, y is 0. And that distinction is going to come up a lot throughout class. So just, be careful about it. And then remember when we had this problem with separable equations where we could integrate and we had a constant? We also had the option of, instead of plugging in the constant, taking those definite integrals. So from this part where we've got the integral of d dx e to the minus 3x times y equal to the integral of 6 e to the minus 3x times x, we can use definite integrals to account for, that's not how you spell account, for the initial condition y of 0 equals 3. And so what that's going to look like is you have the integral of, should be a dx right there, and a dx right there. I'm not writing, it's just missing a d. I'm not writing my integrals carefully like you should. So let's see, we've got 6e to the minus 3x dx. And all of these integrals are with respect to x. So my x value starts at 0, and I want to go up to x. And if it bothers me, I can go ahead and change all my x's to s's to be a little clearer. And then same with on the other side. I've got that this is an integral with respect to x, so it should start at 0 and go up to x. And if I want to change so that there's nothing problematic in here, I could say, okay, use a random variable s. And then it's important to remember that y is a function of x, or in this notation, s. So you'll still have that your derivatives cancel out. So you've got e to the minus 3s, y of s. And you want to evaluate that from s equals 0 to s equals x. And then you've got minus 1/3 6 e to the minus 3s evaluated from s equals 0 to s equals x. So you've just got e to the minus 3x y of x minus e to the minus 3 times 0 y of 0 is equal to negative 2 e to the minus 3x minus negative 2 e to the minus 3 times 0. which is just going to give us e to the minus 3x times y minus 1 times y of 0 is 3. That is equal to minus 2 e to the minus 3x plus 2, which when you solve for y, you move the minus 3 over, so you get a plus 5 on the right-hand side. And then divide through your e to the minus 3x. You've got minus 2 times 1 plus 5 e to the 3x. Same solution as before. Again, only use that method if you want to.